Thank you, Chairman. So first, I would like to thank to Noam and to his colleagues for the invitation and for the possibility to speak here. And I'm going to speak about Luzin-Novikov theorem, and this is a joint work with Petr Holický from Charles University in Prague. So I would like to start with the this version of Luzin-Novikov theorem. Here we have two Polish spaces, X and Y, and we consider a Borel subset of the product of these two spaces. And the set B has the property that any section for any X, we have a section Bx, so this is the definition, so it appears here, is countable. So any section of the set is a countable set. And then the Luzin-Novikov theorem says that B can be covered or can be written as a countable union of Borel sets, Bn, which are contained in B. And each set Bn is Borel, and each section of Bn contains at most one point. So this theorem says that we can cover or we can write the set B as a countable union of countable Borel graphs. Okay. And in my talk, I would like to discuss the possibility whether there exists a quantitative version of this theorem. By this, I mean whether we can have a result of the following type. So, if we know more about, if we know more about the set B, we know that this is in some specific Borel class, whether we can use this information to obtain this decomposition, these sets Bn in some Borel class. Okay. So the answer is no, and I would like to put down the precise statement a little bit later on. My talk will be focused on Luzin-Novikov theorem, but the same approach can be used in disproving a possible quantitative version of Sen-Raymond theorem. So let me state this important uniformization result. Again, X and Y are Polish spaces, and we have a set B, Borel set in the product. And here we assume that any section of B is sigma compact. So this means that any section is a countable union of compact sets. And then the result says that B can be covered by countably many Borel sets, Bn. Bn is a subset of B for any n. So this is as in the Luzin-Novikov theorem, but here any section B and X is compact for every n and X. And again, we may pose a question whether if we know something about B, that it is in some class, Borel class alpha, whether these sets Bn can be chosen in the same class or even or in some prescribed class. And the situation is the same as for the Luzin-Novikov theorem. The answer is no. Okay, so let me state this in a more precise way. So here alpha will be a countable ordinal. And the theorem says that for this alpha, one can find a closed set F in the product of the Cantor space and bare space, such that for every x, the section Fx is in fact 2-point set. So even more restrictive than in the assumptions of the Luzin-Novikov theorem. And F cannot be covered by countably many sets Bn, which are contained in F, such that each Bn is in the Borel class sigma 0 alpha. So this alpha appears here, and the section Bnx contains at most 1 point for every n and x. So this proves a possibility of possibility to have quantitative version of the Luzin-Novikov theorem. Of course, by Luzin-Novikov theorem, we can find Borel graphs with such that the union gives the set F, but necessarily they have to be more complex than just being in the class sigma 0 alpha. Okay, so this is a result related to Luzin-Novikov theorem, and for Raymond result, we have the corresponding theorem too. Again, alpha is a countable ordinal, and for this ordinal we can find a closed set F, again in the product of the Cantor space and bare space, such that for every x, the section Fx is a countable discrete set. So in particular, this is a sigma compact set, and again, F cannot be covered by countably many sets Bn, such that each Bn is in the Borel class sigma 0 alpha. So this is a boldface. Yeah? And the section Bnx is compact for every n and for every x. So me and Petr Holický, we try to solve this problem for some time. We posed this question at several conferences without as an open problem, without success. And at certain moment, I asked Alexander Kekris, I posed this question, and he gave me these two handwritten notes entitled, as you can see. So the results due to Leo Harrington, and so the second one is just 1 page note, and one can find more or less here that that the method from this paper can be used to prove that for any ordinal alpha, ordinal alpha, there is a closed set F in the product of two bare spaces, such that all sections contain exactly 2 points, and there is no function F, such that its graph is sigma 0 alpha subset of F. So this is quite close to the result in theorem 1. There is no proof. So what we made is that we took the method from this manuscript, and we adapted it for our purposes. But the main ideas come from this manuscript. So before starting with presenting some ideas of the proof, I would like to present a version of this theorem or of this question, which can come to mind. And here The theorem 1 remains true if we replace the assumption on the Borel class of Bn's by sigma 0 alpha measurability of the mappings Fn. So in theorem 1, we considered graphs as a subset of the product, and we consider their Borel complexity. But one can ask, one can consider this graph, or one can consider the corresponding mapping giving this graph and consider sigma 0 alpha measurability. Okay? And it turns out that this problem is much simpler. So here we consider mappings, not the complexity of mapping, not the complexity of the graph, and it can be resolved as follows. Let H be a Borel set in the Cantor space, which is not of the class sigma 0 alpha. And then by a standard result, there is an injective continuous function G mapping a closed subset E of the Baire space onto H. And so we consider the graph F of the inverse mapping, which goes from H to E. And since E is closed and F is G is continuous, we have that this graph is closed. So this is a closed set, and with at most one point sections Fx because of continuity. But if we consider covering by some graphs of some mappings, which would be sigma 0 alpha measurable, then we will obtain the contradiction with the complexity of the set H. So this is just this. So there is a huge difference between these two problems. So in the rest of my talk, I would like to indicate some basic ideas. At the end of my talk, it will be they will be presented quite vaguely, but okay. Let me fix some notation. Alpha will be a countable ordinal as before. Script n will stand for the Baire space. C, this is Cantor space, and script s will be the set of all finite sequences of integers. And throughout my talk, I will use also recursive bijection of omega onto omega times omega. So any integer can be considered as a pair of integers. And if Z is from the Baire space, so this is an infinite sequence of integers, then we can apply this mapping to, bracket 0 and bracket 1. We can apply it to Z coordinate-wise. So Z can be considered as a pair of two infinite sequences of integers. I will also use the notion of Turing jump in the following setting. So here U and V are elements from N, and the Turing jump of U with respect to V will be defined using this universal set for sigma 0 1 semi-recursive sets. This epsilon, so this is fixed at the beginning, and it makes some objects epsilon recursive or semi-recursive, and it is also related to this fixed ordinal alpha. And we can iterate the jumps, and we will work with the mapping, which assigns to y an element from the bare space alpha jump with respect to x. So this is the notation, and the strategy of the proof is captured in the proposition 3. So here we have this epsilon, which I vaguely described. And the proposition 3 says that one can find the set E in the product of n times n and a closed set in the product, and a family of functions xi x, where x varies over the bare space, and each xi x goes from the section of E, from x section of E, to the section of F. Okay, and we require for properties. The first two properties concern the set E. So here we require. So this condition is about the section of the set E x. This is a little bit more complicated, but okay. So it expresses that some sections are just two-point sets. So if we have x and k and we consider the section, then this is a two-point set. And the second property is the following thing: that for every x, there is no sigma 0, 1 light phase x epsilon set W in the product of n times omega. So W is in fact a family of recursive semi-recursive sets in x and epsilon, such that each section is covered by the union of these Wn. So as I said, if we consider so this n, so this is a section of this set. So Wn is a subset of n, and it should cover Ex. And secondly, the set of this type. So we consider the intersection with the section of E, and this set contains at most one point for every k and n. So this condition says that such a family with these two properties doesn't exist. So we would like to construct a closed set which is not, there is no, with no uniformization, with no decomposition into Borel sets of certain quality. And here, this is a germ of this this construction. It's the starting point in some sense, that that the set E enjoys this property, but at for very simple sets. But it will be our starting point, and then we will continue. Then we will continue with in constructing the desired set. But this will be the starting point. Okay, so these two conditions concerns the set E. The next condition, Xi1, is related to this family of mappings, and it says that whenever we have a family of boldface sigma 0 alpha subsets of n squared, there is an element A in the Cantor set and W in sigma 0 1 A epsilon. So this is the same situation as here, such that the inverse image of xi A of any B and A is Wn intersection A. And the last condition, it says that that this mapping xi x, okay, more or less it sends these sections to these sections. This is a bijection between, it rises the bijection between any two sections of this type. Okay, let me let me use some pictures to illustrate this result. So here we have just the copy of the proposition 3, and on one side we have this set EE in the product, and okay, if I take K here, it means that I interpret N as omega times N, and I require that that these sections here. So here we have just omega, and so here we have just 2-point sets. So you can see that finally we obtain some set satisfying this condition on 2-point sections. Okay, and we have also a set F, and we have the picture like this. So the mapping xi A goes from this section onto this section, and the property, let me repeat it, the property xi1 says that if we take some family of sets from the class sigma 0 alpha, then we can find some A here, and the corresponding family of sets W, such that we have this reduction. Okay, and the point is that if so, I'm trying to explain the strategy of the proof. So if we assume that we can find these Borel graphs of from the class sigma 0 alpha, then okay, so these sets will be graphs, and if we use this corresponding inverse image, then we will obtain a contradiction with the property E0. Okay, so this is the strategy of the proof. Here I also show the mapping which assigns to elements from N the corresponding jump of the type alpha, and the idea is that we will construct this mapping or this family of mappings in such a way that that this composition, so one, will be continuous, and so it enables us to get the property E1. Okay, so this is where we use the jump. So so we have, in fact, we have two tasks here to do, two objects to construct. The first one is this part. Okay, we have some E as a starting point, and then to construct this these mappings xi A. So let me start with the first item. This is captured in the proposition 4. And this says that there exists sigma 0, 1 epsilon recursive set T alpha. So T alpha is a subset of the space S. This symbol stands for the finite sequences of integers and is a Bell space before, such that the following properties are satisfied. So the first property says that if we take the section, if we consider T alpha the section, then we obtain a tree. So we can view T alpha as a parameterized family of trees. The second property says that if we consider infinite branches, this is the body of Tx alpha, and we will consider just the second coordinate. Yes, as I introduced this bijection, and any sequence of integers can be split into two sequences using this mapping. So if we take this part of Z, then this is just a singleton, and the third property is that the jump, the type alpha for X, okay, is recursive using this part. So the branches of Tx alpha contains a complicated object. Then the set E is constructed very easily. We simply put together the bodies of these trees. Okay? And then, okay, so this is just a repetition, then it works. So, so this proposition 4 provides the solution for or the construction for the first part. Yeah? We have our starting point. Okay, now I would like to say a couple of words about construction of xi x. So we have T alpha and E from proposition 4. And we are going to construct a closed set F and this mapping, as I said. And as I have already mentioned, we would like to do in such a way that if we compose this mapping with and we apply the jump of the order alpha, then still we will have a mapping which will be recursive. So this will accomplish the property xi1. So what we are going to do is this. At the beginning, we have this T alpha x. This tree comes from the proposition 4, and we would like to do many things. We would like to construct some intermediate trees and some auxiliary mappings among them, such that at the end we will construct the mapping, the desired mapping xi x. The construction doesn't go from one tree to another, we have to, but rather we have to construct the whole chain in some sense at once, yeah? Because at each step of the construction, okay, so in each step of the construction, we apply two principles of the construction. I will describe them in a minute. Some part of the chain has been already constructed. This is this starting point, and then we copy some branches of this tree to another trees according to some rule, and also we will modify them. Okay. So, but throughout the construction, the main objects we will work with sequences of integers and sequences of finite sequences of integers. So the latter ones can be viewed as partition sequences or decomposed sequences of integers. So besides these trees and some auxiliary mappings, we will for any branch which appear in the construction somewhere, we will also construct the corresponding decomposition. Okay, so let me describe the decomposition of sequences which we consider. So suppose that T is a finite sequence of integers. So here we have T. And then we will consider only the compositions of the following form. Okay, so we start with some sequence tau, then there will be an integer, so a sequence of the length 1, and there will be another sequence, and so on. So we have integers which we identify with sequences of length 1, and okay, so they are here, and then we have these eta sequences. Okay, they can be longer than just the sequence of length 1. And we introduce also a special element, so let me call them minus, okay, so different from sequences. Okay, so and if this is a decomposition of T, if this is a decomposition of T, then the concatenation of these sequences should be T. Okay, if there is a minus, then we interpret minus as the empty set, and okay, it doesn't appear in the concatenation. And decomposition of T, so this is the paper, should provide some information about Turing jumps relative to X for some Z, which extends T. Okay, so if we have T and the corresponding decomposition here, and if some eta sub I is different from minus, and this means that the Turing jump with respect to X, the position I is 1 for every Z which extends T. Yeah, so extending T and extending or building a new decomposition, it provides some information about the jump of the final sequence. It goes step by step, and if eta sub I is minus, then okay, we don't know what. The sequence is too short to say something, but this says that a certain test of this condition failed. Yeah? So we just so this is the aim, and also these intermediate trees will have complicated branches. So this one part of the branch should contain the jump of the level beta. Okay. So now, at the end of my talk, I would like to say something about how these two methods, how these two principles are applied to construct the desired chain of trees and the resulting mapping Xi. So here for compiling, I would like to simplify my situation a little bit. And so if we assume that alpha is omega, so in fact this is the case in the Harrington's manuscript, then this is rather easy. So instead of general ordinal, here we have just omega, and here this intermediate trees are indexed by natural numbers, and this principle is very simple. If we take nth tree and we restrict it to sequences of length at most n, it will be the same, will coincide with the tree tx omega restricted to sequences of length at most n. So this is the first step of the construction, and we simply take certain parts of this tree and we copy them to these trees. If we work with a general ordinal, then the situation is a little bit more complicated. We have to introduce some auxiliary structure on the ordinal alpha, and which says what to copy from which tree to which one of which length and so on. But here this is rather simple. Okay, so now suppose that we have already. Okay, so we are in the process of the construction of txn, but suppose that we are in the situation that we have already constructed t, which is in txn, and together with the corresponding decomposition, which, as I try to explain, speaks about the corresponding jump of sequences extending t, and suppose that a natural number m is given, and now our task is to decide whether this extension will be in txn or not, and if this is the case, then also we would like to determine the corresponding decomposition. Okay. Okay, first, we look at the one part of this concatenation, yeah? And it should approximate nth jump. So, in some sense, okay. So here we have a prescribed test, which where we can check whether this is good approximation or not. And we also would like to have that this part is already in the 3txn plus 1. Okay? And if this is not the case, then we do not include this extension into txn, and we are done. If this is the case, that these two conditions are satisfied, we continue, and we consider we considered an auxiliary decomposition. This is just a temporary decomposition, which may be with the final one or not, it depends. Okay. So here we have the original decomposition of T, and here we added M and this symbol minus. Okay, and so this last step in the construction, so I would like to try to use this picture. So I have to omit out of details, but where we are. So look. So here, this represents this this temporary decomposition. Okay? So each circle is an integer, and if there is a double, so we use this 0 and 1 part. So here we have this original sequence T, and if we apply concatenation, then and we connect these together, then we will obtain a sequence of integers. But here these blocks represents these items, these items in the decomposition. And here we added the natural number m. It has two parts, yeah? And at the end the symbol minus. And now we are looking for the possibility that if we concatenate, okay, so we should find some minus, and we can take this part, and we consider concatenation. It is longer than the initial sequence T, and we can ask whether this test about the jump is satisfied at this position or not. If this is the case, then okay, we put the sequence Tm into the tree Txn, and we create a new decomposition. So the beginning up to this sequence is the same as here, and this creates a new sequence in the decomposition. And if this is not the case, then we simply use this temporary decomposition as the final one. Okay, so this is the Harrington's construction, Harrington's approach, which works. I omitted a lot of details. For example, we should also consider some minimality, because and okay, so in some sense we are in the case 2 if this decomposition satisfies some minimality condition, to be able to use this to define mapping xi of x. Okay, so thank you for your attention.